Hello, thanks experts and professors for listening this presentation. I'm the presenter, Fang from ZT Corporation, and I'm very honored to present the paper with the title Gaze-contingent Rendering in Virtual Reality. The paper is the result of the collaboration between the ZT Corporation and Hong Kong Polytechnic University, and also Shanghai Jiao University and the Shanghai University of Sports. The research background is that currently, most virtual reality things are far behind the real world. The mainly is that when we focus on the quality and also on the fluence, we will find that although we want to reach the such quality of the real world, but the really experience is a little far from that. This is because the limitation that we always have insufficient graphic computing performance of the computer. And really, considering the network bandwidth and also the computing load, we need to trade off between the high picture quality and high fluence. What we are doing is that we focus our research work in the area of the when visual field is smaller than the display area. So we can consider some trade-off between the high picture quality the viewer can experience and also the high fluence regarding the content. Let us firstly introduce the main part of this paper. Firstly, we combine the salience information and also the head motion information to predict the focus of the field of view in real time. This is the basement of our work. Since based on such information, we will assign different rendering priority to the objects in the scene. The scene in the focus of the viewer will use a high priority, and the object is outside the focus, but in the scene, will assign a lower priority. According to the different priorities, we use the different rendering algorithms, which considering the experience of the viewer regarding our objects. The focus area of the visual fields in the focus is rendered with the high position, and the outside such area, the lower position processing is performed. What we consider our contribution of the paper is that, firstly, we completely based on the software implementation of our work. So it really can improve laterally based on the improvement of our algorithm. And secondly, the system structure is streamlined and also very efficient. It can achieve higher rendering effects under general hardware consideration. So we can really doing our work without the consideration of our rendering hardware, the limitation. And also we think it really proposes the future development direction of VR rendering, which will really improve the user experience based on the limited hardware resources, and also it will really based on a really software implementation. This research work is really the continuing of our previous work. We have really published some work related to that in the previously. The first is established a model for viewpoint prediction in immersive video, and also the paper regarding use head rotation information to improve the accuracy of saliency prediction. And according to currently, VR devices have also begun to implement grading rendering in practical application. The system structure can refer to the picture below. As illustrated, the system is firstly collect the information of motion information of the device sensors. Then, the salience information is calculated from this scene screenshots. The result will as an input into the SCSI model, which can be referred to the paper A Data-Driven Eye-Head Coordination Model for Real-Time Gaze Prediction. And then, when we get the prediction of the viewpoint position, we will pass this information to the full Foveated Rendering program. As mentioned previously, the focus or the basement of our system structure is the viewpoint prediction. Since we really disclose the principle behind the movement of the eyeball and also the information of the head, it really has some strong correlation between these two information, as illustrated in the below calculations. And also, we can refer to some tools of deep learning, such as SAM Reslet, the model, deep learning model, to help learning and doing the prediction of the saliency. We really design this algorithm to help to predict the saliency value of the things and can reach the performance of 250 milliseconds per frame. The scheme of implementation is based on the principle of mask-based foveated rendering, MBFR. We really divided the rendering image into two areas, as mentioned before. The higher priority for the focused area, and we want to reach a high position, and also the area outside of the focus. You can also divide it into more areas regarding to the different priority. For the higher priority area, when we're rendering, we're really doing nothing special processing for considering the computing. But when the lower priority area, we will really discuss some pixels and only reconstruct them given the average value from the neighboring pixels for really reduce the computing load. For evaluate the performance and effects of our system architecture and also the achievements of our algorithm, we set up the hardware system of the experiments as below. As the Windows of our operating system and the Intel i7 as our main CPU, and also the rendering hardware as a common NVIDIA GeForce rendering card. And we use the Oculus Rift as our VR headsets. We're doing our experiment focus on the two parts. The first part is to verify the prediction results of the viewpoint prediction algorithm and also the implementation. We can see the results is listed as below. The green dots indicates the line of sight of the participants, of the viewer, and the red dots indicate the position of the line of the sights. We can see it's really close and has enough accuracy. The second part of the experiment is considering the rendering effects and efficiency given our implementation scheme. It is based on the no expect effects rules as we have evaluated based on a subjective perspective. And we list the rendering calculation time with different scenarios in the table 1, which we list the total time, drawing time, and also the time spent on the image effects. And we can see with the different status of the foveated rendering, and we really can decrease the overall render time performed about 14% as achievements of our system. Thank you. That's all my presentation, and thank you for listening. And later is the question time. Thanks.